Okay, so today I'm going to talk about 9 rules for writing Python extensions with Rust and Rayon. And this is something I learned when I upgraded a bioinformatics package that was using C++ and switched the C++ part to Rust. And here's kind of the story about how that happened. 10 years ago, I was at Microsoft Research as a research programmer, and our project was called FastLim, which did statistical analysis of DNA data. And that was written primarily in Python, but with parts of it in C++. I maintained that, we maintained that over the years, but 2 years ago I retired, and kind of looking for a retirement project, I decided to kind of upgrade the open source FastLim and do some other work. So the first part of that was to move it from Python 2 to Python 3, which was necessary to keep it relevant. And then I got a user request for a piece of it, which was called the bed reader, which is just a Python library for reading a particular kind of DNA data file from the disk. So that went fine. Then 1 year ago, I hit what can only be called C++ OpenMP hell. So OpenMP, I wrote down here, it's a data parallel library for C++. That's not really true. OpenMP is a compiler option. It's a different mode of running a C++ compiler. And when you run it, it brings in or requires a runtime library, but it's actually changing your compiler. So to be a good Python library, bedreader actually compiled all of the C code, C++ code on Windows and Mac OS, and we would have wanted to do it on Linux if it had been practical. That meant we had to pick a particular compiler, say the Microsoft or Intel compiler, which means we needed to pick a particular OpenMP library, because it turns out there are competing ones. There is an Intel one, and there is an LLVM one, and they're not the same. There are also versions of the Intel one where if you have the wrong version, it doesn't work. So when I tried to include everything I needed so my users could just download and run, it sometimes worked fine. But if they had another library, maybe a more important library than mine, that also used OpenMP, they might be using the LLVM version of that. And when you try to do that, try to use 2 versions, the Intel and the LLVM at once, you get a nice Intel error saying it looks like you're using another OpenMP, and that doesn't work. And there was just no nice solution to that. Python's always a bit worse than Rust in that it doesn't have a notion of a lock file or additions of the language. That things can change out from under you. And here's a case where now another library that my users might be using is incompatible with my library. So I wanted to learn Rust anyway. And when I saw that Rust could do some multi-thread parallelism without bringing in a runtime, it seemed like a wonderful thing to try. So about a year ago, I replaced all our C++ code with Rust and Rayon, which I'll talk about. Over the course of that, then reflecting on it just last month, I said, yeah, I should kind of tell people how it went and give some advice. And it's like, well, I could just call it, here's some vague advice, but it sounds a little more interesting and a little, sound like I'm a little more emphatic. So I'm going to call it 9 rules. I don't really care if you follow the rules, and I don't really think they're all rules, but I'm going to give it as a prescription, just because it makes it more interesting. This should, of course, be of interest to anyone who wants to write Rust code that Python code can use. I'm hoping it's also of some interest to just general Rust programmers, because part of the process was to try to find what best practices in Rust were for the kind of programming I was doing. So related to working with 2D arrays, having nice errors in Rust, doing the data parallel work, especially data parallel multi-threading work that actually returned errors instead of just eating them up, allowing users to control the number of threads, and I have to be very careful how I spell that, and how to use generics, Rust functions that can work on efficiently on different types, not to be confused with genetics. So let me, before we get to the rules, I'll have a couple background slides. So let me talk about the bed reader. And by the way, this link will take you to the source code. So the bed reader is a Python package for reading and writing DNA data in the Plink bed format. The format can be thought of as a 2D array. Whoops, I started to use my mouse. A 2D array, there, where the rows are individuals who are identified with, for some reason, 2 strings. The columns are DNA locations, which are identified with 1 location. Those are called SNPs. They're places on the DNA that people are known. Different people might have different DNA value there. So in this example, we've got 400,000 individuals and DNA data for 1.5 million locations. That POS array above tells something about each DNA location. Specifically, it'll tell which chromosome a location is on, and it has 2 values, 2 different ways of measuring location. So the actual value in the array can be 0, 1, 2, or missing. And that has to do with whether you get the most common value that people have there or the second most common, and whether you get, and you'll get 1 from mom and 1 from dad, but you won't know which one comes from which. So there are 4 values. On the disk, each value is represented with just 2 bits. So it's a binary format that's tight. But when the user reads the data, they're going to want, well, we're not going to give it to them in bits. So they can have it as an 8-bit int, or often, probably most often, they'll want it as a float 32, a single float, or a double float, a float 64. And that's because often after reading this data, the next thing they're going to do is divide by the, subtract off the mean, or divide by the standard deviation, or put it in, just do some kind of numerical work with it. So a floating point array is what they'll often want. A feature of bed reader that I think makes it nice is that you don't have to read just 1 column of data at a time, and you don't have to read all the data at once. You're allowed to give say which subset of the individuals you would like data for, and which subset, and or which subset of the DNA locations you want. And it will do a random access and only read that data from the disk, and only return the data you're interested in. So it's very common to say, I want the data for all the individuals, but for the first 100 DNA locations, that's 1 chunk. Now the next 100 DNA locations, the next chunk, and so on. And that's easy to do. And yeah, this bed reader is used by our tools, but it's also used by other tools. And sometimes users will just use it directly if they just want to read a bed file. They're not doing, or they're doing their own thing with the data after that. Let me motivate what Python extensions are. So Python is my 2nd favorite language. It's one of my 2 favorite languages. I don't like to pick between them. I love it because it's very readable. It's very flexible. It has maybe the best packages, not the best package system, but the best actual packages in the world. But the problem is it's really kind of slow. In my hierarchy, the way I think things are at the top, we've got C++, C, and Rust. And one step down in the middle, we have C# and Java. And at the bottom, we have Python, just kind of going slow. But because it's slow, from the beginning, people have written libraries for it in faster languages, usually C or C++. So for example, look above my head, the NumPy project, which is the largest project for scientific and array computing in Python, is written 2/3 in Python, but 1/3 is in C, 1% is in C++, and there's even 0.1% in Fortran. And as long as you're doing things, operations that can be done in big chunks, like a matrix inversion or a matrix multiply from matrices that are in memory, even in Python, the result's going to be fast because it's using these faster languages to actually do the big operation. But of course, the problem with C or C++ is the safety issues that motivated Rust. You can have pointer problems, you can run off the end of arrays, and if you're multi-threading, you can have all kinds of problems, including race conditions. So the obvious thing to anyone who's interested in languages and has been writing these extensions in C or C++ and they hear about Rust is, can we write them in Rust? One more slide before we go to the 9 rules. So let me just outline the approach I'm advocating. The approach is that at the Python level, we're going to have what I'm going to call a nice Python function. And this is a function that a Python user of a library would be happy to use. It's going to allocate any memory that's needed. It's going to take and output native Python types. It's going to allow users to use the dynamic types that are typical for Python. I'll talk about that later. It'll allow users to limit the number of threads if they want to. If it creates an error, the errors it produces will be standard, nice Python errors, and it'll have testing in Python. That nice Python function will call what I'm calling a Rust translator function, a function written in Rust, whose only job is to do what it has to do so that we can call the nice Rust function. The nice Rust function is a function that doesn't know anything about Python. It will use native Rust types. Where appropriate, it'll use generic functions. It'll do multi-threading if that's appropriate. It'll know about Rust errors, and it'll return nice Rust errors if there are errors, and it will be tested in Rust. So the rest of this talk will go over the 9 rules that kind of put some, elaborate on this outline, this approach. And you can also see an article I wrote last month in the online magazine toward data science, which is in medium.com. I'll hopefully share out the slides. There's both the link to it, but I'm also including a friend's link. If you don't have a subscription to Medium, you don't have to pay to see it. Okay, rule number 1 is to put the Rust and the Python code in one project. And specifically, the file should be pretty much just like this. So at the top level, we're going to have general files that you'd have for any project, the README file, for example. The next section of files will be regular things you'd expect to see in Rust, the cargo.toml, the lib.rs. I'm going to recommend in this scenario that you also create a Rust file called Python modules, and another one. I like having my tests in their own file, so test.rs. On the Python side, things look almost normal. We'll have the regular Python configuration files. We'll have a folder, bed reader named after the project, and then the default Python file, a init.py, and then some other files that are appropriate to whatever we're doing. And underneath that, there'll also be a folder for the Python tests, and underneath that, there'll be a folder for the Python test data. And if we're doing, I'm doing this on GitHub and using GitHub Actions, so there's also a GitHub continuous integration script. The one thing about the Python files that's different is normally a Python project that's setting up to be a library would have something called setup.py that would give some metadata about the project, and would also, if there was extensions, would actually have the command lines for calling, say, the C compiler. Because of some changes in Python packaging, we don't have to do that anymore. So instead of setup.py, we can have pyproject.toml, and it can say that instead of using the default build system, we want to use a special build system called, and I can't pronounce this necessarily correctly, Maturin, and this is a build system especially for Rust code, and we'll talk about that presently. Very presently. Rule number 2, to use, just use Maturin and Py03. So Maturin is a package for Python, actually written in Rust, but it's you install it like another Python package. If you're a Python program, you say PyPI Maturin, and it installs. So it's for building extensions. It's for doing a bunch of things, but among other things, it's for building extensions via Py03. Py03 is a Rust crate. It does lots of things, but among other things, it supports writing extensions for Python. And when we use them, we'll set up our Rust cargo.toml. Here's some of the things that are in the dependencies I have. So here's the Py03, and we're telling it we want the extension feature. I really like this library for making it easier to define and handle errors in Rust, called thiserror. Rayon is the library for doing data parallel multi-threading. ndarray is the Rust library crate for handling multi-dimensional arrays, especially in my case, I'm caring about 2-dimensional arrays. And I want the feature that lets it work well with Rayon. And in my testing, I'm also including a feature that lets me compare 2 arrays and see if all the values in them are close to within some approximation. NumPy is a crate that lets Rust use the NumPy arrays that are defined in Python. And finally, for testing, I use temp test directory so I can output things to a directory and not have them stay there forever. And then, yeah, inside lib.rs, the default Rust file, I'm going to tell it that I also have a Python module rs and a test rs. So I've hinted at this before, but we'll go into some details. Rule number 3 is to have Rust translator functions call nice. Have Rust translator functions call nice Rust functions. So this is this is an example of a Rust translator function. Python can call it directly. I'm a little unhappy with what I did with the names here, but Python thinks the name is read underscore F64, and Rust thinks the name is read underscore F64 underscore pi. I think if I had to do it over again, I would give them the same name. I may fix that. Notice the arguments to this function. It's a string. It's a couple integers that have to do with the size of the data file. It's a bool. Those are all fine. The next input is a 1D array of indexes. It's the indexes of the individuals for whom data we want to read. So that's a Python array, 1D array. And likewise, that next array is an array of the DNA locations that we want to read as stored in a one-dimensional Python array. And the final thing is the thing we're going to fill, and then that'll be how we get the results back to Python. And that's a two-dimensional Python array where the values are double precision floating point numbers. And we'll talk about num threads later. So these are all types that Python is comfortable in creating and passing. So all this translator, the main work of this translator function is it has to convert these Python types into kind of more standard Rust types. So on a 1D array, we call the read-only command. That gives us another version of it. And then we call the .asSlice method. And that'll change this Python thing, 1D array into of integers into a Rust slice of integers, which is kind of the more standard way to do it. And of course, it doesn't have to reallocate any memory or anything. It's just a different way of looking at the same memory. Likewise, we need to convert the Python two-dimensional array into the Rust two-dimensional array. That unfortunately has to be done with an unsafe, but I don't know what you can do about that since the Python array really is kind of unsafe. But after we do that, now it's a Python two-dimensional array. And we'll talk later about why this says F64 and why this says pi error and what we're doing here with the num threads. Those are all things to look at later. Rule number 4 is pre-allocate whatever memory you need if it's at all possible in Python. So here's the Python, the nice Python function I was referring to. The first thing it does is import some of the Rust functions written in Rust, including read F64. Then we define it. I'm leaving out some code here. The thing we want to fill is this two-dimensional array of, in this case, floats. So we just do a kind of standard Python thing. We say we want an array of this many rows, this many columns. We want it to be this order. That has to do with whether it's row major or row minor, two ways of organizing the rows and columns in memory, and what type we have here, float 64. Then we'll tell it which Rust translator we want to use. In this case, reads F64. And then we just call whatever we just said, and we pass this stuff in. Because we allocated the memory here, we don't have to do it on the Rust side, which is very convenient because this memory, sorry, I'm pointing at the wrong spot, because the memory we allocate in Python is garbage collected by Python. I believe there actually is a way to allocate garbage collected memory in Rust that Python can then garbage collect, but why bother? And even if we did that, we want our ultimate file reading thing to be agnostic as to how this memory was created. so that we can also use, be perfectly happy filling Rust two-dimensional arrays that don't have anything to do with Python. Rule 5, and there's some comments on the side about this error. So do nice Rust error handling and do nice Rust and do nice Python error handling. So let me give examples from the code about what I mean here. So here's an example error that we might see. We're in our nice Rust function, which is called read no alloc. And the first thing we're going to do is open the file name the user gave us. But what if that file doesn't exist? Then the question mark will make the function return with the same error that file open returned, which will be of type standard IO error. And if we make our function read no alloc return a type of result bed error plus, then we can return the standard error, but only if we define bed error plus to encompass the standard error that we know we might get. And we do that with the code on the box. Oh, I got it on the left. So we import from this error library's error something. I don't actually know what that is. And then we define our Rust enum called bed error plus, and it includes standard IO error, which we'll call IO error. It also includes some other enums that define errors. One's called bed error, which we'll see on the next slide, and another's called thread pool error, because we'll be doing something with a thread pool later that might return an error. So this is every error our function can possibly return. And yeah, so this is called wrapping errors. It's in Rust by examples, but it's not listed as like the right way to do it. It's listed as one of 2 ways to do it. It's the second one. And they don't tell you should just use this error to make all this stuff short like this. Instead, they give long, long examples of what you have to do if you're not using this error. So use this error. The one problem we have is a Rust error doesn't look much like a Python error. So we want in our translator function to convert the bed error plus to Py error, which is the library's class for the Python error. And we can do that just by defining an implementation of a convert from method. And it says you input an error of type bed error plus, and then we'll do a match statement on that. If it matches that IO error that we're talking about on the slide, then translate that to a Python IO error and give it the same string error message as it had before. Python has like 5 main classes of errors: IO, value, I don't know, something to do with threading, stuff, indexing errors. So I'm not showing all the code. The match statement goes through some other cases. It tries to find every possible index error it does find every like indexing error related to indexing. And when that's the case, it creates a Python index error with the right string. And when all else fails, for any errors that it hasn't specifically said what to do, how to translate them, it translates them into a Python value error, and then includes, but with the nice string that should give some details of the error. So let's look at one more example of error handling. So this is the example where we want to create an error. We want to define an error of our own type. And this particular one happens when you open a Plink bed file. The first 2 bytes in the file should be 2 particular bytes. And if they're not those 2 bytes, then you've opened the wrong kind of file. It's not a bed file. And in that case, I say, well, if you see it and it's not the 2 bytes we were expecting, then return the bed error called ill-formed with the name of the file in it. That's all you have to do, except elsewhere, the second white box, we say we have another enum called bed error, and it has an error whose message will be ill-formed bed file header is incorrect or linked is wrong, and then it'll have something plugged in where that curly 0 curly is, and that'll be the file name parameter that we saw up above, and this will be called a bed error ill-formed error. And now we define as many of these as we want. These are our custom errors plus those system errors, and now we've covered all the errors, and they all have nice appropriate parameters to actually be useful to people, and they'll all get translated to Python. So yeah, for both languages, we now have both standard and custom errors. They all have good messages. This is specifically how I'm doing it with this extensions, but honestly, I can't think of any reason not to do this in any Rust program, to use this error and define errors to this specificity. So there's nothing more fun. I'll just say, I'll read it out loud. Rule 6, multi-thread with Rayon and ND parallel returning errors. So there's nothing more fun than to run some numeric job and to actually be able to use all your CPUs if you have a multi-CPU machine. There's nothing worse than to have it running for minutes and minutes at, like on my machine, at 12% because it's only working on one processor. It's like, just use the other processors. So Rust makes it very easy to do data parallel multi-threading. If you have work where you're treating all, say, columns of a matrix the same, then Rayon and this other library make it very easy to do multi-threaded operations on it. We'll see examples on the next 2 slides. So Rayon is Rust's general data parallel multi-threading library, and ND parallel is the specific subpiece of the the multi-dimensional array library that knows about how to do Rayon on its arrays. The one trick here is that we should return errors. Some of these multi-threading things, you start the work and it's doing all the things on the different columns, but it assumes that you're not going to have any error. And if you do, you should maybe just panic and crash everything. We don't want to do that. If there's an error, like a value that we're writing out that's not the 0, 1, 2 or missing, we want to return an error to the user saying that you had an illegal value. We don't just want to panic and crash. So I'll look at 2 approaches to doing. I'll give examples of an approach to using Rayon and ND array parallel that let us return errors. Sorry, it's a bit involved. So here's the first one. This is from Rayon. It's using the parallel bridge method, and particularly the try for each. So starting at the top, let's suppose, this isn't shown, but suppose we have an iterator that'll try to read an entire column's worth of binary data. So this is all the data for all the users for one DNA location. And we're just going to iterate. So it's going to go jump, 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 read the binary data as fast as it can. And as an iterator, send that to the rest of this code. So the first thing we're going to do is zip it with the array, with the columns of our output array. So now we're going to have a column of binary data and a column and our output array column, and those will be zipped together. And this will be run on one thread, and the next one will be run on another thread, and however they schedule it, some number of them will all be being run in parallel. And the thing we're going to do is we're going to call try for each, And what that does is it just runs a block of computational code that you want with no return value at all, except if there's an error or not. So I'm not going to go through this code. This is just code to take the kind of compacted bits that our data is in and turn them into the values that we want. In this case, probably the floating point values, or return an error. The nice thing about try for each, even though it's working in parallel, if any of the parallel work returns an error as fast as it can, it will close down all the work and then return the error that it saw. So it won't be doing any extra work, and it'll be reporting the error. So in this case, that works very nicely. But one of the best commands, if you're doing parallel work over a bunch of arrays, is the ndarray's parallel azip macro. And it's nice because you can give it a whole set of arrays or pieces of arrays and say, I want you to, you can have 1 or 2 or 3. In this case, we have 5, that I want it to run through the columns of each one together, working kind of like it did before. So instead of having to do whatever it was, like 5 zips, now I just have this one command, and it says take the stats row from the stats array, take 1 observation from the unobserved array, take 1 sum from the sum array, take 1 sum squared from the sum squared array, and take 1 result, I call it a pointer, it's not really a pointer, 1 result pointer from the result list. And you do that, you can put your code there in the curly brackets and do whatever computation you want, and it's fine. The only problem is, I mean, it's wonderful. It's like the shortest, most concise way to represent that you want to do this work in parallel. The problem is it can't return errors. So what I'm recommending is that one of the arrays that you pass in that you want to work on is a result array, and it does nothing but record the result of every, in this case, column's bit of work. And when we're all done, along with having our main output array, in this case, having to do with figuring the average value for each column and the standard deviation for each column, it'll also have whether the computation for each column, what the result code was, whether it was okay, or if there was an error. And when we're all done, we can then check that result list to see if we got any errors. And in fact, we can check it with the try for each. So we're in the parallel iterator, so we can actually try it. We can look for any errors in parallel. And this, of course, we're going to do all the work, even if there was an error early on, which is too bad, but hopefully errors are relatively rare. So it won't kill us. So rule 7 is to allow the user to control the number of parallel threads. On the Python side, but I really think everywhere, users should always be able to control the number of parallel threads, either because they're maybe running on a shared machine that they're not yet allowed to use all the threads on, or because they're running some of their own other work and they don't want it to use up the whole machine on this job, or just because they're like watching YouTube videos on the side and it's interfering with their enjoyment. So on the Python side, what I do is I have an optional parameter that's how many, called num threads, and the user can set how many threads they want to use. If they don't set it, it'll look at some environment variables and see whether it's been set with the environment variables. If it hasn't been set with environment variables, then it'll use all the processors on the machine. And to get this to work inside Rust, we're going to assume we have this num threads that Python is passing in, and then we're going to call create pool with the num threads, which will create a thread pool, and then the thread pool object has an install method. Let me back up here. This thread pool isn't defined I defined it here. It's just a little helper function. So you give it some threads, and it calls the standard Rayon thread pool builder. If that succeeds, then it returns the pool. And if it doesn't succeed, it returns the error. And then finally, this install method, given that we have a thread pool, calls a lambda expression with no parameters. So we just call our nice Rust function here. And whatever number we set here, Rayon will make sure that everything called inside these curly braces doesn't use more than that number of threads. And yeah, I'm doing this in the translator function. Thinking about it, I would actually, if I was making this into a Rust library, I would move it into the Rust part, because I think all users should be able to control their thread count. Okay, 2 more to go. Rule 8, translate Python dynamic types to Rust generic functions. So in Python, if a user has a choice, like whether the array will contain integers or this kind of float or that kind of float, we just let them have a parameter called dtype, and they can specify what output type they want their array to have. And if they don't specify one, it'll default to something like float 32. And in the Python function, we can just look at this and see, is it int 8? If it is, use the int 8 Rust translator function. Is it float 64? If so, use the read f64 translator function. If it's float 32, use the Rust translator read f32 function. And if it's none of these, then raise a Python error with a little message saying what's wrong. And now that we've said which reader we want to use, we just call the reader with our file path and our other arguments. So now down here, we actually, instead of just, I'm only showing one of the Rust translator functions, but there's actually 3. There's this one for f64, but there's also one for f32 and 8-bit integer. What's interesting is, even though there's 3 and that's duplicate and that's redundant, they all call the same nice Rust function, read no alloc. And it's a generic function that can work on any of those types, because it works on a type calledtout, which can be instantiated to any of those 3 types, or any type that has these the listed traits. And the way it knows which type it's being called on is both with the type of the values in the ndarray and the type of the missing value. So if you give it a missing value of float 64, it'll know that you want your result to be float 64. The last slide. Sorry, the last rule, and there's one more slide after this. So finally, it's very important to follow rule number 9. Have Rust and Python tests. Python is a wonderful scripting language. It makes writing tests super easy. So it's tempting to just do all the tests in, if you're going to be doing stuff in Python anyway, to just do all the tests in Python. But I don't think that's sufficient. I think there should also be a full set of tests in Rust. The advantage this gives you is it makes the Rust development much more fun, because you can actually run stuff in Rust. You can set breakpoints in the debugger and work interactively. It also, right now, there's not much demand that I know of for a Rust crate for reading these Plink bed files. But if there was, then we've already got most of the library that we need for it, and most of the tests. And a nice thing is the way that if you set up the files the way that was recommended in Rule 1, then both the Python tests and the Rust tests can access any test files that are in the bedreader test data folder. And one thing I didn't know how it would work or not, but at least with Visual Studio Code, it's perfectly happy to have two different languages, both with their own tests. So here's a little snapshot, and the top are 55 Python tests that it's all passed, and then there's a little splitter, and below that is all my Rust tests. And I can run them. I can run them both at the same time if I want. So let me summarize. Rust is a great language for writing Python extensions. It gives us the speed that motivates writing extensions in the first place. It gives us a safe language. It gives us a language with built-in data parallel multi-threading without compatibility problems. Thanks to the libraries that have been provided, it's compatible with Python NumPy arrays, Python errors, and lots of other Python data types. You should follow these rules, and if you do, you'll get great code on both the Python and on the Rust side. And that's the end of the talk.